The moon is the one object in the sky every human civilization has looked at, studied, and thought they understood. And the strangest part is that the closer we look, the less it matches what we thought we knew. It was supposed to have gone geologically silent 3 billion years ago. But recent data tells a very different story. The surface is cracking and shifting, while the interior remains warm enough to cause tremors. Water has also been detected in unexpected environments, and traces of volcanic activity are younger than the age of the dinosaurs on Earth. If the moon went cold 3 billion years ago, why does it keep behaving as if it didn't? Everything we assumed about the moon turns out to be the beginning of a much more unsettling story. For 400 years, the story of the moon was simple. Galileo pointed his telescope at it in 1610 and saw craters, flat plains, and long shadows stretching across grey rock. He named the dark patches Maria Seas because from a distance, they looked like oceans filling ancient basins. They weren't oceans. They were lava fields flooded by volcanic eruptions billions of years ago, cooled into vast, dark plains of basalt rock. But the name stuck, and so did the idea behind it. The moon was a place where things used to happen. Past tense. A world that had its moment burned bright and went quiet. That narrative held for centuries. It was reinforced by every new observation. Every mission confirmed it. Every sample brought back by Apollo astronauts, 840 pounds of rock and soil, collected across 6 landings, between 1969 and 1972, returned a consistent verdict: old, dry, inert. The rocks were ancient beyond anything found on Earth, some dating back 4.5 billion years to the earliest days of the solar system. The soil was described by geochemists as 100 times drier than the Sahara Desert. 100 times. The Sahara, which feels like standing inside an oven with no exit, was practically a rainforest compared to the chemistry of lunar regolith. So the consensus hardened into certainty the way conclusions do when every instrument points in the same direction. The moon formed in a violent collision between early Earth and a Mars-sized body roughly 4.5 billion years ago. The debris from that impact coalesced into a sphere. It was molten volcanic, chaotic, a glowing ball of liquid rock visible from space. Then, over hundreds of millions of years, it cooled. The way a freshly poured concrete floor cools and hardens, except on a planetary scale and over timescales that make human history look like a single sentence in a very long book. The volcanoes went quiet. The interior solidified. And sometime around 3 billion years ago, the last geological activity faded out, leaving behind the frozen, cratered surface visible from Earth with the naked eye every clear night. That was the accepted picture. Textbooks printed it. Universities taught it. Planetary science courses opened with it as foundational context. And honestly, it made physical sense. The moon is small, about a quarter the diameter of Earth, and smaller bodies lose heat faster because they have more surface area relative to their volume. A small stone dropped into cold water cools faster than a large rock. The physics said the moon should have gone cold long before Earth did. The math checked out. The samples confirmed it. Case closed, except it wasn't. The first crack in the story came not from a new discovery but from old data that nobody had looked at carefully enough. The Apollo missions had left seismometers on the lunar surface, 4 of them deployed at different landing sites between 1969 and 1972. These instruments quietly recorded seismic signals for 8 years, transmitting data back to Earth until the program was shut down in 1977. Scientists analyzed some of it, published some papers, and then the funding ended and the recordings went into archives. Decades later, researchers went back to those recordings with modern computing power and new analytical techniques. What they found reframed the entire conversation about what the moon actually is. The moon had been shaking, repeatedly, measurably, in patterns that did not look like random noise or the random patter of meteorite impacts. 28 shallow moonquakes were documented in those 8 years of recordings, events ranging from magnitude 2 to magnitude 5 on the Richter scale. For context, a magnitude 5 earthquake on Earth is strong enough to crack plaster, rattle windows, and knock objects off shelves. Not catastrophic, but entirely real and detectable without instruments. And crucially, 6 of those 28 quakes happened when the moon was at its farthest point from Earth in its orbit, the point where Earth's gravitational pull creates maximum lateral stress on the lunar crust, like squeezing a rubber ball, not from both sides equally, but with a slight twist. The moon wasn't just shaking randomly. It was shaking in response to Earth's gravitational stress. In response to us. That is not how a frozen, inert world behaves. A world that stopped being geologically active 3 billion years ago doesn't have a stress response to orbital mechanics. It doesn't flex under gravitational loading. It doesn't generate fresh fractures in its crust or produce seismic signals that correlate with the positions of another planet's tidal force. Those are the behaviors of a world with something still going on inside it, something warm enough to deform, something under enough internal pressure to crack something alive, in the geological sense of the word, even if not in any biological one. And once scientists started looking at the surface again with that understanding with the high-resolution cameras of the Lunar Reconnaissance Orbiter, a spacecraft that has been mapping the moon in extraordinary detail since 2009, imaging the surface at resolutions down to about 0.5 meter per pixel, which means it can photograph objects the size of a dining table from lunar orbit. They started seeing things that the old narrative simply couldn't accommodate. Cliff-like formations running across the ancient terrain, not the kind of soft, rounded hills that billions of years of micrometeorite bombardment produce as everything slowly erodes and smooths out. These were sharp, clean edges, unweathered surfaces, the geological equivalent of a fresh cut versus a healed scar. On Earth, features like this would tell a geologist immediately, this is recent. In lunar terms, recent means within the last 50 million years, which sounds ancient by any human measure, but remember that the moon is 4.5 billion years old. 50 million years ago, in lunar history, is like finding a wall in your house that was apparently built last week in a building you thought had been abandoned since the Bronze Age. There were thousands of these formations, thousands of geological features scattered across a world supposedly frozen for 3 billion years that are young, that show evidence of recent formation. That could, for all current data, can determine still be forming. Consider what that actually means when you sit with it, not as an abstract fact, but as a statement about the gap between the picture we constructed and the reality that picture was supposed to describe. We had the samples, we had the photos, we had the physics, and we still missed the fact that the moon has been geologically active, measurably, provably, in ways visible from orbit, throughout the entire span of recorded human history. Every civilization that looked up at the moon and called it eternal and unchanging was looking at a world that was the entire time slowly cracking under its own internal pressure. Every astronomer who mapped it as a dead reference point was mapping something that was quietly shaking, venting, and reforming at scales too slow for any single human lifetime to detect. The picture that's emerged from the last 15 years of lunar research is not a minor correction to the old model. It's a fundamental revision of what the moon actually is. Not a frozen relic, but a world in slow motion. Not a static backdrop, but a geological system still running just on a clock that measures time in millions of years rather than human lifespans. The question this raises immediately is what's driving it? What is the physical process that keeps the moon active when every calculation said it should have stopped? The answer to that is simpler and more visual than you might expect. And it starts with something as ordinary as a grape sitting too long on a kitchen counter. Every rocky world in the solar system starts the same way, violently, catastrophically hot. When the moon formed 4.5 billion years ago from the debris of a planetary collision, it was essentially a sphere of liquid rock, a magma ocean covering its entire surface, glowing orange-white against the darkness of the power early solar system. If you could have seen it from Earth at that moment, which you couldn't because Earth was also largely molten, it would have looked less like the pale disk we see tonight, and more like a second sun. Smaller and dimmer, but radiating heat, visible from millions of miles away. Over hundreds of millions of years that heat radiated away into space. The surface cooled first, forming a thin crust, the way a skin forms on hot pudding as it sits on the counter. Then the interior began to cool from the outside, in layer by layer over geological timescales, measured in hundreds of millions of years. And as it cooled, it shrank. This is basic physics, the same principle that makes a metal bridge slightly shorter in winter than in summer. Heated material expands. Cooled material contracts. Rock follows the same rule. As the moon's interior lost heat, the material compressed, the volume decreased, and the entire sphere became measurably smaller. Scientists estimate the moon has contracted by roughly 50 meters in radius over its recent geological history, which means the circumference of the moon has shrunk by more than 300 meters compared to what it was hundreds of millions of years ago. 300 meters of circumference lost to cooling. On Earth, that kind of contraction is handled by the tectonic system. The crust is broken into plates that can slide past each other, subduct under each other, crumple into mountain ranges, a constant flexible adjustment to the stresses of a cooling, changing interior. The moon has none of that. Its crust is a single continuous shell, rigid and brittle like the hard shell of a boiled egg. When the interior contracted beneath it, the shell had nowhere to go. It couldn't compress smoothly, so it did what brittle shells do. Under compression, it broke. In specific places across the crust, the compressional stress exceeded the structural strength of the rock. One section of crust was pushed up and over the adjacent section, creating a steep ridge, a stair-step cliff visible from orbit. These are called thrust fault scarps. They look in satellite images like wrinkles on a dried fruit, which is exactly the right analogy because the physics is identical. A grape shriveling into a raisin develops wrinkles because the skin is too large for the reduced interior volume. The moon's crust, too large for its contracted interior, developed wrinkles too, except the moon's skin is rock and the wrinkles are cliffs. The Lunar Reconnaissance Orbiter has found thousands of these fault scarps spread across the entire lunar surface. Some are modest 10 or 15 meters high, a few kilometers long. That 10 or 15 meters might not sound impressive, but standing at the base of one on the airless lunar surface, looking up a sheer rock face of that height, with no atmosphere to soften the view and no familiar context for scale, would likely feel more like confronting a cliff than stepping over a towel curb. Others are larger. The Lee Lincoln Scarp in the Taurus-Littrow Valley reaches heights comparable to a 5-story building running for kilometers across the landscape. The Apollo 17 astronauts, Eugene Cernan and Harrison Schmitt, encountered that scarp directly during their December 1972 surface operations. Their route to a geological sampling site crossed the scarp's face, and they had to navigate their lunar rover in a zigzag pattern to find a traversable slope up the cliff. They noted it, photographed it, and reported its presence. It was catalogued as an interesting topographic feature. For decades, the full significance of what they were driving over wasn't recognized. They were crossing a crack in a world in the process of contracting, a physical record written in stone of the moon's interior cooling and pulling inward, a process that was supposed to have finished 3 billion years ago, but had apparently continued right up to within the last 50 million years. And possibly much more recently than that. In January of 2024, a study published in the Planetary Science Journal brought this from geological abstraction into immediate practical relevance. The research team, led by Thomas Waters of the Smithsonian Institution, confirmed that the strongest shallow moonquake ever recorded by the Apollo seismometers had its epicenter somewhere in the lunar South Polar region. The exact location, NASA has designated for the Artemis crewed landing missions, and the South Polar region is densely covered with fault scarps. The modeling in that study found that shallow moonquakes capable of producing strong ground shaking equivalent to a magnitude 5 event sustained for minutes rather than seconds are not hypothetical for that region. They are consistent with the geological evidence on the ground. To put that in practical terms, the landing sites currently being evaluated for the next humans to walk on the moon sit inside or adjacent to active seismic zones generated by a world still contracting under its own cooling. The engineers and mission planners at NASA are now formally incorporating lunar seismic risk into their structural requirements for surface habitats and equipment, not because it's a theoretical possibility, but because the geological record makes it a quantifiable probability. For comparison, Mercury went through the same cooling and contraction process but far more dramatically. Mercury's thrust fault scarps reach heights of 3 kilometers and lengths of 1,000 kilometers. enormous structures visible as mountain-like ridges across its surface. That scale tells scientists that Mercury contracted far more than the Moon did, which means Mercury's interior was far hotter to begin with, likely fully molten throughout when it formed. The Moon's relatively modest scarps are consistent with a more moderate thermal history, a partially molten formation, a slower cooling curve, a more gradual contraction still running today. More gradual meaning it isn't finished. There's a quality to this that takes a moment to absorb properly. The Moon looks from Earth exactly as it has looked for the entirety of recorded human civilization. The same face, the same craters, the same dark plains and bright highlands. Nothing about its appearance from 384,000 kilometers away suggests that anything has changed in billions of years. Yet, underneath that familiar surface, a physical process is still running, compressing, cracking, adjusting on a timescale, slow enough that no single human lifetime, no single civilization, no single geological era, by human reckoning, would detect any change. But real, measurable, active, the Moon is shrinking, not metaphorically, not historically. Currently, and every time a fresh fracture opens in its crust, every time an old fault line slips under accumulated stress, the whole world shakes, sometimes gently, sometimes with enough force to be relevant to engineering calculations for the people who will live there, which leads directly to the next layer of this story. Because those shaking events, the moonquakes themselves, are not all caused by the same thing. And one of the 4 distinct types of moonquakes that the seismometers recorded reveals something about the Earth-Moon relationship that is both mechanically fascinating and slightly difficult to process emotionally. The Moon shakes in part because of us. A moonquake is not like an earthquake, and the difference matters more than it might initially seem. On Earth, when the ground shakes, the seismic energy travels through rock, soil, and water-saturated sediment at every level of the crust. All of that water permeating the rock, filling microscopic pores flowing through underground aquifers, acts as a natural shock absorber. It converts seismic energy into heat through friction at a molecular level, rapidly dissipating the wave. A magnitude 5 earthquake on Earth typically runs its course in 20 to 40 seconds. The ground moves, the energy bleeds away into the water-rich crust, and within a minute, the event is over. If you weren't paying attention, you might miss it. A moonquake at the same magnitude can last for 10 minutes. 10 minutes of continuous ground motion from a single seismic event. The reason is the absence of that shock-absorbing water. The Moon's interior is extraordinarily dry. The Apollo samples confirmed that the deep rock is essentially anhydrous, without water all the way down. Seismic waves entering that dry, rigid rock find almost nothing to absorb their energy. They bounce. They reflect off internal boundaries. They reverberate through the crust, the way sound reverberates inside an empty cathedral, not dampened by soft furnishings and human bodies, but bouncing off hard stone walls, sustaining long after the source stopped. Apollo astronauts listening to early recordings of moonquake data reached for a specific word to describe what the instruments captured: ringing. The Moon rang like a bell after a strike, like something metallic, like something with a hollow quality to it. That quality, the dry, ringing, wave-preserving nature of the lunar interior, is the acoustic backdrop against which all 4 types of moonquakes play out. The first and deepest type originates more than 600 kilometers below the surface. For context, the Moon's total radius is about 1,700 kilometers, so these quakes are happening more than a third of the way to the center. At that depth, the rock is under immense pressure, compressed by the weight of hundreds of kilometers of material above it. And yet, it fractures. It slips. It generates seismic signals measurable at the surface. When researchers plotted the timing of these deep moonquakes against the Moon's orbital position relative to Earth, the pattern was immediate and unmistakable. These events cluster around 2 specific orbital positions when the Moon is closest to Earth and when it is farthest. Those are the positions where Earth's tidal gravitational force creates either maximum compression or maximum tension in the lunar interior, like squeezing a stress ball at its narrowest point and then pulling it from both ends. Alternately, once per orbit, every 27 1/3 days, without stopping for 4.5 billion years. Earth is mechanically working the moon's interior from 238,000 miles away. The gravitational kneading applied continuously across every orbit generates enough stress in rock 600 kilometers deep to cause it to crack and slip. The moon's interior is being deformed repeatedly and measurably by the planet it orbits, which means that the moon's geological activity is not simply a consequence of its own internal cooling. It is partly a consequence of its relationship with Earth. We are, in a very real mechanical sense, contributing to the moon's geology from a distance equivalent to traveling around Earth's equator almost 10 times. The second type of moonquake, shallow, at depths of 20 to 30 kilometers, comes directly from the fault scarps described in the previous chapter. This is the contraction process made audible. When a section of crust slips along a thrust fault, the released energy propagates outward as a seismic wave. These shallow events reach magnitudes up to 5.5, strong enough to shift loose surface material to destabilize slopes in permanently shadowed craters to pose genuine engineering challenges for any structure built on or near a fault zone. The January 2024 study modeled one specific fault scarp in the Artemis candidate landing region and found its formation was consistent with a moonquake in the magnitude 5 range, generating strong ground shaking across an area of many tens of kilometers. To put that scale in human terms, a circle of many tens of kilometers radius drawn around the candidate Artemis landing sites would encompass an area larger than many major cities. Ground shaking across that entire area sustained for several minutes from a single slip event on a fault that may still be active. That's the engineering reality that the updated geological picture of the moon creates. The third type of moonquake is almost poetic by comparison. It comes from the surface itself, from the extreme thermal cycling that the lunar crust undergoes every month. With no atmosphere to buffer temperatures, the moon's surface swings from negative 170 degrees Celsius in the 2-week lunar night to positive 120 degrees in the 2-week lunar day. That's a temperature range of nearly 300 degrees across a single sunrise, which on the moon takes roughly 2 Earth weeks to arrive after the long darkness. Rock expands when heated contracts when cooled, and at that temperature swing the shallow crust develops hairline, fractures, shifts, and settles, generating small seismic pops. Apollo astronauts reported hearing these through the structural frames of their landing modules, a faint irregular ticking as the rock around them adjusted to the rising or setting sunday. The fourth type is the simplest meteorite impact. A rock from space strikes the surface, kinetic energy converts to heat and seismic waves, the ground rings outward from the impact point. The moon receives roughly 1 meteorite impact per square meter of surface per day, in the form of dust-sized particles, and larger impactors at decreasing rates. Each one sends its small seismic signal into the interior. What the combined picture presents is a world that is seismically active on 4 separate mechanisms simultaneously: internal cooling, tidal stress from Earth, thermal cycling, and external bombardment. None of these are catastrophic individually, but together they mean that the moon's surface is never truly still. Something is always happening at some scale somewhere. The quiet grey disk that has served as a symbol of stillness and constancy in human culture for millennia is at the physical level continuously active. There is one more dimension to the tidal relationship worth examining before moving forward, because it connects to something broader. The deep moonquakes driven by Earth's tidal force generate friction in the lunar interior. Friction generates heat, not a large amount relative to the moon's total thermal budget, but not zero. The same tidal interaction that is slowly transferring orbital energy from Earth to the moon. The same force that makes the oceans rise and fall is also depositing a small but continuous supply of heat into the moon's deep interior. Earth is in part keeping the moon's interior warmer than it would otherwise be if the moon were orbiting alone in the void. The relationship between the two bodies is not one-directional. The moon pulls on Earth's oceans. Earth pulls on the moon's interior. Each is continuously shaping the other in ways so slow they're invisible on any timescale, shorter than millions of years, but so consistent that the accumulated effect over geological time is enormous. And the accumulated effect has produced something that no one in the early days of lunar science thought to look for, because looking for it would have required believing first that something was still active enough inside the moon to push it to the surface. Something visible from Earth. Something that monks and astronomers and astronauts all saw over centuries of observation and described in terms that science spent a long time dismissing before the data made dismissal impossible. On the 18th of June 1178, 5 monks at Canterbury Cathedral in southern England were standing outside after evening prayers watching the sky when they saw something they had no framework to explain. The moon was a thin crescent just past new, a slim curve of light low in the western sky after sunset. By their account, the upper horn of the crescent suddenly split in two. Between the two halves, something ignited, described in the chronicle they later wrote as fire sparks and a reddish glow like a struck flint throwing light in multiple directions. The horn then rejoined, and the crescent returned to normal. The entire event was brief enough that they could observe it, clearly unusual enough that all 5 of them noted it, and striking enough that it made it into an official written record that survived 850 years. For most of that time, historians treated the account the way they treat most unusual medieval observations, as a curiosity, probably a misidentification, possibly atmospheric distortion, or the tricks that a bright crescent moon can play on, eyes adjusting from darkness. The monks were credible witnesses by medieval standards, but medieval witnesses saw dragons in northern lights and omens in comets. Without corroborating physical evidence, the Canterbury account sat in the category of interesting but unverifiable. Then, in 1976, a geophysicist named Jack Hartung cross-referenced the date, the described location on the moon's surface, and the nature of the observed event against geological data. The match was striking. The description was entirely consistent with a major meteorite impact, the kind of impact that would have blasted material high above the lunar surface, generating a plume visible from Earth as a brief flash of light at the exact position described. And on the northeastern quadrant of the moon there is a crater called Giordano Bruno, 20 kilometers wide, with ejecta rays that are unusually fresh, unusually bright, unusually unweathered compared to the ancient softened craters surrounding it. By crater counting and ray analysis, Giordano Bruno is young, recent, possibly formed in the late 12th century. The Canterbury monks may have watched a rock from space hit the moon 1178 years ago from their monastery garden in England. That's one event. A single night, a single impact, a brief flash in the dark that happened to have 5 literate witnesses and a chronicle that survived the centuries. But the broader phenomenon, those monks observed what planetary scientists now call transient lunar phenomena, or TLP, is not a one-night story. It is a database of over 2,200 documented events stretching back to 554 AD, drawn from observers on every inhabited continent, spanning 14 centuries of recorded history. The events take many forms. Reddish or orange glows localized to specific crater regions, lasting from a few minutes to over an hour. Bright flashes of white light, too brief to be anything other than an impact or a sudden chemical reaction. Hazes and apparent mists that obscure surface detail in a limited area, making the sharp crater edges soft and indistinct for minutes before clearing. Blue or violet colorations along crater rims. Temporary darkenings of regions that are normally bright. Events covering areas ranging from a few kilometers to hundreds of kilometers across, appearing and disappearing, with no permanent change to the surface visible in subsequent observations. William Herschel, the astronomer who discovered Uranus, one of the most credible observational scientists of the 18th century, reported seeing what appeared to be a volcanic eruption on the moon in 1783. His standing in the scientific community was such that the report received serious attention. It was debated, examined, and then quietly shelved when follow-up observations found nothing unusual at the reported location. In retrospect, the event he described, a localized bright area with a reddish tinge along a crater rim, matches the profile of a gas release event with enough precision that dismissing it entirely seems more like institutional reflexes than scientific judgment. In 1963, 2 professional cartographers at the Lowell Observatory in Arizona trained observers with instruments under careful viewing conditions, recorded vivid orange, red, and pink colorations along the rim of Aristarchus crater. This was not a fleeting impression. It lasted long enough for both observers to describe it independently, to change eyepieces, to consult each other, to make careful notes. The event was so well documented that it effectively restarted formal scientific interest in TLP after decades, during which the topic had been considered too anecdotal for serious study. Apollo astronauts in lunar orbit reported seeing unusual glows in the Aristarchus region from their command modules. Aristarchus is not a random location on this map. It sits on a plateau in the Oceanus Procellarum that is, by lunar geological standards, anomalous in multiple ways. The terrain is younger than the surrounding region. It is associated with extensive volcanic structures, lava channels, dome-like formations collapse, features suggesting underground lava tubes. The crust in that region may be thinner than average, and the underlying rock appears to be compositionally different from the ancient highlands. Most significantly, Aristarchus accounts for over 60% of all credible TLP reports in the entire database. Not 50%, not 40, 60, one location among the hundreds mapped across the lunar surface generating the majority of observed transient events. That concentration is not random, and the explanation for it connects directly back to everything discussed in the previous chapters about internal heat, crustal fractures, and the moon's continuing geological activity. The leading scientific explanation for the majority of TLP events, not meteorite impacts, which account for the brightest flashes, but the longer duration glows, hazes, and colorations, is outgassing. The moon's interior, still warm enough to generate seismic activity, still under pressure from overlying rock, and from Earth's continuous tidal kneading, periodically releases gases through the fractures and fissures in its crust. The primary candidate gas is radon, a radioactive element produced by the slow decay of uranium and thorium deep in the lunar rock. Radon is a gas at lunar surface temperatures, and when it escapes through a crack and reaches the surface under direct sunlight, it interacts photochemically with the regolith, potentially creating a visible glow. When it accumulates briefly above a fissure before dispersing into the vacuum, it can create the hazy, mist-like obscuration that multiple observers have described. The statistical evidence connecting TLP to outgassing is not circumstantial. A Columbia University researcher named Arlen Krotz spent years applying rigorous statistical filters to the TLP database, removing reports that showed clear observer bias that came from single observers with no corroboration that occurred, in patterns more consistent with psychological expectation than physical phenomena. What remained after those filters was a subset of events that appeared consistently from independent observers at specific locations across centuries of observation. When he mapped those robust TLP sites against the moon's known outgassing sites locations, where the Apollo 15 and 16 orbital instruments and the later Lunar Prospector spacecraft detected direct emissions of radon from the PRO's surface, the geographic overlap was striking enough to calculate the probability of the two datasets aligning that closely by chance was approximately 1 in 10,000. The places where people have been watching strange lights for 14 centuries are the places where radioactive gas is measurably escaping from the interior. That's not a coincidence. That's a signal that the old instruments were too limited to read, and the new ones confirmed. The moon is exhaling. Not dramatically, not continuously, but periodically when internal pressure builds enough to push gas through whatever fractures are currently open, and those fractures release their load. The exhaled gas rises briefly through the vacuum, catches sunlight, and becomes momentarily visible from Earth as a glow or haze before dispersing. Then it's gone, leaving no trace, and the surface looks exactly as it always has. And the next observer who happens to point a telescope at Aristarchus sees nothing unusual and concludes that the previous report must have been a misidentification. But the pattern across 14 centuries of reports filtered for reliability and mapped against physical measurements says otherwise. The moon is not silent. It never was. And if it's releasing gases through fractures in its crust, if its interior is warm enough and pressurized enough to periodically vent material to the surface, then it's also doing something far more consequential. Something that directly affects every future plan humans have made to live and work on the moon. Something that, when it was first confirmed, reversed 50 years of scientific consensus in a single announcement. When the Apollo astronauts returned from the moon in 1969, they brought back the most carefully examined rocks in the history of science. Geologists, chemists, mineralogists, and planetary scientists from institutions across the world queued up to analyze those samples with every available instrument. The question of water was treated as essentially settled before the analysis was complete. The expectation was so strong that some researchers reportedly joked the moon was drier than their laboratory equipment. When the results came back, the joke seemed appropriate. The lunar rocks were anhydrous without water in a way that exceeded even the driest materials found on Earth. Geochemists described the moon as 100 times drier than the Sahara Desert. The Sahara, a place where survival without water supply is measured in hours, was a comparatively wet environment. That conclusion stood unchallenged and largely unquestioned for 40 years. The moon had no water, full stop. The revision began in 2009, not from a single dramatic discovery, but from 3 separate spacecraft, India's Chandrayaan-1 and 2 NASA missions, Cassini and Deep Impact, independently detecting a spectral signature associated with hydration across sunlit lunar terrain. Not water necessarily. The instruments available at the time couldn't distinguish between actual water molecules and hydroxyl, which is a single oxygen atom bonded to a single hydrogen, chemically different from the 2 hydrogen. 1 oxygen structure of water, but something was there. Something wet. The discovery was announced, acknowledged as significant, and then largely interpreted as a surface interaction between solar, wind, hydrogen, and oxygen-bearing minerals in the regolith. Interesting chemistry, but not water in any meaningful sense. Then in 2020, NASA's SOFIA Observatory settled the question with a measurement that couldn't be argued with. SOFIA was, in its design, one of the strangest scientific instruments ever built. A modified Boeing 747 commercial jetliner with a 106-inch infrared telescope mounted in a hole cut into the rear fuselage, flying at altitudes up to 45,000 feet to get above 99% of Earth's atmospheric water vapor, which would otherwise absorb the specific infrared wavelengths needed to identify water from a distance. It was essentially a flying observatory designed to look at things in wavelengths that water in Earth's own atmosphere would block, and when it pointed at the moon's sunlit surface, it detected the specific infrared signature of molecular water. 2 hydrogen atoms bonded to 1 oxygen atom, chemically distinct from hydroxyl in the Clavius crater. One of the largest penning impact structures on the near side of the moon, sitting in full direct sunlight. Not ice, not hydroxyl, water. The concentration was equivalent to roughly 1 12-ounce bottle of water dispersed through a cubic meter of lunar soil. For context, the Sahara Desert contains 100 times more water per volume, but the Sahara has an atmosphere, weather systems, some degree of humidity, and is protected from direct solar ultraviolet radiation and the constant stream of charged particles that the solar wind delivers to the airless moon. On a world like the moon, any water on a sunlit surface should be destroyed within hours by that radiation broken apart at the molecular level. The hydrogen stripped away the oxygen, recombined with minerals in the regolith. The physics of an airless world in direct sunlight says water should not be able to persist there. And yet it does. Something is generating it. Something is trapping it. The mechanism is not fully understood, which is a phrase planetary scientists rarely use about basic questions, like why does this substance exist here, but the moon keeps producing them. 2 leading hypotheses exist. The first, micrometeorites, the constant rain of tiny space particles striking the moon's surface at high velocity, roughly 1 impact per square meter per day, generates extreme localized heat at the impact point. That heat can drive chemical reactions between the hydrogen in the impacting material and the oxygen in the surface minerals, producing water molecules. Some fraction of those molecules, before they can be destroyed by radiation, become embedded in the amorphous glass that forms when regolith is shock melted by an impact. Trapped there, shielded from direct solar exposure, they persist. The moon collects water 1 micro-impact at a time. The way a dry sponge placed in a light mist doesn't get wet dramatically, but accumulates moisture molecule by molecule. The second hypothesis points inward. The Chang'e 5 mission, which returned samples from the Oceanus Procellarum in December 2020, provided chemical evidence that the interior of the moon is not as dry as the Apollo samples suggested. Among the returned material was an unknown mineral, now formally designated ULM1, in which water accounted for over 40% of the mass. Not trace amounts, not parts per million. Nearly half the mineral's weight was water chemically bound within a crystalline structure that doesn't form on the surface. It forms under the pressure and temperature conditions of the deep interior, and it reaches the surface through geological processes. Volcanic eruptions slow upwelling through fractures, the same pathways that allow radon to escape. The moon may be generating water from within through the same internal processes that drive its geological activity. Water from space collected one micro-impact at a time. Water from the interior migrating upward through cracks. Water frozen in permanently shadowed craters for billions of years, undisturbed since before complex life existed on Earth. The permanently shadowed regions at the poles tell a separate and equally dramatic part of the story. These are craters deep enough that their floors receive no direct sunlight. Not just for weeks or months, but permanently for geological timescales. Some of these crater floors haven't seen a single photon of direct sunlight in billions of years. The Lunar Reconnaissance Orbiter measured temperatures inside some of them at negative 230 degrees Celsius, colder than Pluto, colder than anywhere else in the inner solar system, cold enough that water ice deposited there from cometary impacts or volcanic outgassing billions of years ago has simply never had any reason to leave. It sits there frozen, accumulating slowly, a geological bank account that has been collecting deposits since before the first multicellular organisms appeared on Earth. In February 2025, NASA's Prime 1 drill, part of the Intuitive Machines IM-2 mission, became the first instrument specifically designed to extract and test subsurface material from the lunar South Polar region for ice content. Not detect from orbit, not infer from spectra, physically drill, extract, and analyze. The goal was to determine whether the ice is present in forms and concentrations actually usable for human purposes. Because this is where the science connects to something with direct human stakes. Water on the moon is not merely a geological curiosity. In the economics of deep space, water is the most valuable substance imaginable. Launching 1 kilogram of water from Earth's surface to lunar orbit costs somewhere between $10,000 and $50,000, depending on the launch system. Water already present on the moon in extractable form eliminates that cost entirely. Split water with electricity from solar panels, and you get hydrogen and oxygen rocket propellant and breathable air. A lunar base with access to local water doesn't need to carry every kilogram of life support from Earth. It can be at least partially self-sustaining. The moon transforms from a remote, expensive dead end into a refueling station, a waypoint, the first stop on a route to everywhere else in the solar system. Water made the moon a gateway rather than a destination. But everything about the water story on the moon, where it comes from, how it persists, how deep it goes, requires the moon to have a thermal history more complex and more prolonged than anyone initially assumed. It requires an interior warm enough to produce and migrate water-bearing minerals. It requires a fractured crust through which material can travel upward. It requires geological processes that are still in some form running. And if that's true, if the interior is warm enough and the geological processes are active enough to produce and migrate water, then it becomes possible to ask a question that the standard timeline made pointless. If the moon went cold 3 billion years ago, the question has no interesting answer. But if the moon's interior retained heat far longer than predicted, if the cooling curve was shallower and slower than the models assumed, then something else becomes possible. Something that was ruled out so long ago that most planetary scientists stopped thinking about it. What if the moon's volcanoes never fully stopped? The standard timeline for lunar volcanism was one of the most confidently held conclusions in planetary science. The moon's volcanic history was divided cleanly into 3 phases. In the first billion years of its existence, from formation at 4.5 billion years ago to roughly 3.5 billion years ago, intense volcanic activity flooded the large impact basins on the near side with wave after wave of low-viscosity basalt lava. The dark plains visible from Earth tonight are the surface record of those eruptions, vast lava floods that filled basins hundreds of kilometers across, cooling into smooth, flat surfaces that look from distance like dark seas. This was the Moon's fire age. Hot, active, prolific. The second phase saw the rate of eruptions decline as the interior cooled. Between 3.5 and 1 billion years ago, volcanism became less frequent, less widespread, smaller in scale. Isolated eruptions continued in certain regions, adding thinner layers to the existing lava plains, but the dramatic basin flooding events were over. By approximately 1 billion years ago, the last lava flows solidified. The interior had cooled below the threshold for generating eruptions. The volcanoes went dark, and from that point, the Moon entered a permanent state of geological stasis, the frozen crater-accumulating surface that the Standard Model described. That was the accepted timeline, and it was considered well supported, not just by theoretical cooling models, but by direct radiometric dating of Apollo samples which consistently returned ages in the billions of years for all the clearly volcanic material they could identify. The case seemed closed with physical evidence as well as theory. Then the Lunar Reconnaissance Orbiter started sending back high-resolution images of the Maria, the ancient dark volcanic plains, and researchers started finding things that didn't belong in a 1 billion-year-old geological record. Scattered across those ancient plains were small, shallow depressions unlike anything else on the surface. Their floors were irregular, a mix of smooth, rounded mounds, rising a few meters above a rougher, hummocky lower level, like the surface of a landscape where something had partially collapsed or partially extruded. The edges of these depressions were sharp and fresh, without the rounded, weathered appearance of billion-year-old features. And most tellingly, they had almost no impact craters on them. On the Moon, the number of craters on a surface is a direct measure of its age. Older surfaces have been exposed to bombardment longer and accumulate more craters. These features had crater counts consistent with ages of less than 100 million years. They were called irregular mare patches. About 90 were eventually identified across the near side, all associated with volcanic structures, all showing the same anomalously young crater counts, all displaying the sharp, fresh-looking topography of recent geological counts. Origin: 100 million years old. In a geological system that was supposed to have gone quiet 1 billion years ago, that's not a minor discrepancy that's like finding a building in the ruins of an ancient city with plumbing that was installed last year. The timescales don't fit. Either the age dating method is wrong for these specific features, or the standard timeline needs substantial revision. The scientific community debated this vigorously and productively. One alternative explanation proposed that the features might be ancient, formed billions of years ago, but composed of unusually porous volcanic material that doesn't retain impact craters the way solid rock does. On this reading, the features would be old but appearing young, a geological disguise rather than a genuine age anomaly. It was a reasonable hypothesis consistent with known properties of volcanic foam-like materials, and for about a decade the debate remained genuinely open. In September 2024, a paper in the journal Science resolved at least part of it, not by theoretical argument, but by direct measurement of physical material. The Chang'e 5 mission had returned to Earth in December 2020, with 1.5 kilograms of lunar soil from the Oceanus Procellarum. Scientists had been analyzing that material across dozens of research programs. One group focused specifically on glass beads in the sample, tiny spheres, each smaller than the period, at the end of this sentence, formed either by volcanic eruption or by meteorite impact. The challenge was chemical forensics, distinguishing volcanic glass from impact glass based on composition and isotopic signatures bead by bead in a sample containing thousands of them. After nearly 4 years of analysis, 3 beads were identified as volcanic. 3 out of thousands of impact-generated spheres, a concentration so low that finding them required methods described in the paper's commentary as isolating a needle in a haystack. The dating method applied was uranium lead radiometry, one of the most precise and reliable techniques in geochronology, based on the predictable decay of uranium isotopes into lead at known rates. The result: 123 million years old with an uncertainty of plus or minus 15 million years, volcanic glass, formed in an eruption on the Moon 123 million years ago. 123 million years ago is not ancient by planetary standards. It is not the deep past. It is the early Cretaceous period on Earth, the era of Tyrannosaurus rex, of Triceratops, of vast inland seas, covering what is now the American Midwest, of flowering plants, just beginning to diversify and spread. The continents were in positions not entirely unlike today. The Atlantic Ocean was younger and narrower, but already recognizable. Birds were diversifying from their dinosaurian ancestors. While all of that was happening on Earth, the moon was erupting. The finding directly contradicts the 1 billion year cutoff that the standard model required, and it shifts the question from whether recent lunar volcanism occurred to why it occurred. The answer likely involves the unusual concentration of radioactive elements in the Oceanus Procellarum region, thorium, uranium, and potassium, in concentrations significantly higher than other parts of the moon. These elements generate heat through their natural decay. Regions with higher concentrations retain thermal energy longer, staying warm enough to produce eruptions after the rest of the moon's volcanic system has shut down. Oceanus Procellarum appears to be one of these thermally privileged regions, a hotspot in the geological sense, persisting long after the moon's global volcanic era ended. The irregular mare patches, the Chang'e 5 volcanic glass, the IMP feature Ina, with its possible 33 million year age together. They describe not a single isolated eruption, but a pattern of continued low-level volcanic activity in specific regions of the moon sustained far beyond the canonical cutoff, driven by locally elevated concentrations of heat-producing radioactive elements. The moon's fire never fully went out. It retreated to the places with the most fuel and burned slowly, quietly in patches of terrain that looked ordinary from orbit, for hundreds of millions of years past the point where it was supposed to have stopped. And perhaps those fires are not yet completely extinguished. A question that the planned Dimple mission, designed to land directly on the IMP feature Ina in 2028 and perform the first in-situ radiometric age dating on the moon, is being sent specifically to answer. But volcanic activity, seismic activity, outgassing, water production, all of these are internal processes. They say something about what's happening inside the moon. There is one more phenomenon to examine, one more strange feature of the lunar surface that requires a completely different explanation. One that points not to the moon's present geology, but to its ancient history. A history of something the moon once had and lost. Something whose ghost is still written on the surface in patterns of light and dark visible from Earth on any clear night with a small telescope. Something that, when you understand what you're looking at, is one of the more striking demonstrations in the solar system of physics operating at planetary scale over geological time. In 1649, the Italian astronomer Francesco Maria Grimaldi was methodically mapping the moon's surface through his telescope, cataloguing craters and plains and mountain ranges, when he encountered something that didn't fit any of those categories. In the vast, dark plain of the Oceanus Procellarum, the ocean of storms covering roughly 2.5 million square kilometers on the moon's western near side, there was a bright marking. Not a crater which would cast a shadow, not a mountain or ridge which would have elevation, not a bright ray system from a fresh impact which would radiate outward in straight lines. This was something else. An irregular oval shape roughly 65 kilometers across, bright white against the dark basalt, with curved, sinuous streaks of lighter material extending from it in sweeping arcs like brush strokes, or like cream being stirred into dark coffee at the moment the two are first meeting. Grimaldi named it Reiner Gamma after a nearby crater. He had no explanation for it, which was appropriate because no adequate explanation would exist for the next 350 years. Reiner Gamma belongs to a class of features called lunar swirls. There are dozens of them scattered across the moon's surface, some large and complex like Reiner Gamma, some smaller and simpler, some on the near side and several on the far side, where they were discovered only when spacecraft first photographed the moon's hidden hemisphere. They share two consistent characteristics. First, they are regions of unusually high surface reflectance, brighter than the surrounding terrain, interlaced with darker areas in curved flowing patterns. Second, and less obviously, every lunar swirl is co-located with a localized magnetic anomaly in the lunar crust. That second characteristic is the key to understanding everything about them, but to understand why it matters, you first need to understand what happened to the moon's magnetic field. The Moon today has no global magnetic field. Earth's field is generated by the movement of liquid iron in its outer core, a deep dynamo, continuously powered by the temperature difference between Earth's inner and outer core, circulating molten metal that generates electromagnetic fields extending tens of thousands of kilometers into space. The Moon's interior, smaller and cooler, does not have an active dynamo. It hasn't had one for a very long time, but it did once. Evidence locked in the mineralogy of ancient lunar rocks, the precise alignment of magnetic domains in basalt crystals that could only have formed in the presence of a strong external field, confirms that the early Moon had an internally generated magnetic field active approximately 4 billion years ago. That field was strong, possibly comparable to Earth's present field in intensity. It persisted for perhaps 1 billion years before the interior cooled below the threshold for sustained dynamo action and the global field collapsed. When the field collapsed, it didn't leave nothing behind. The rocks that had crystallized during the field's active period retained their magnetic signatures, the way iron filings, frozen in cooling resin, retain the pattern of whatever magnetic field was present when they solidified. These ancient magnetized basalts are distributed unevenly across the lunar crust, more concentrated in some regions than others, depending on where volcanic activity was most intense during the dynamo era. They are remnants of a planetary magnetic field that no longer exists, fossilized in the rock, maintaining their local fields passively, without any energy input for 4 billion years. These localized patches of magnetized crust are the magnetic anomalies, and their effect on the Moon's surface is precisely what creates the swirls. The solar wind, a continuous stream of charged particles, mostly protons and electrons flowing outward from the Sun at roughly 400 kilometers per second, is the primary agent of space weathering on the Moon's surface. When solar wind protons strike the regolith, they drive chemical reactions that produce nanophase, tiny particles of metallic iron nanometers in size, dispersed throughout the surface material. These nanophase iron particles are extremely efficient at absorbing light across visible wavelengths. They darken the surface. Over millions of years of continuous exposure, the Moon's surface darkens progressively from whatever lighter color it originally had to the gray-brown tones we observe today. Every part of the surface, exposed to the solar wind for long enough, becomes gray. The darkening is slow, continuous, and cumulative geological sunburn, operating across billions of years. In regions where a crustal magnetic anomaly is strong enough, the local field deflects the incoming solar wind, redirecting the stream of charged particles around the magnetic pocket rather than allowing it to strike the surface directly. Think of it as a small umbrella in a steady rain. The surface under the umbrella stays dry. The area just outside the umbrella's edge, where the rain is redirected and concentrated, gets wetter than it would have without the umbrella. On the Moon, the umbrella is a patch of ancient magnetized rock, a few kilometers to tens of kilometers across. The rain is the solar wind. The dry patch under the umbrella doesn't darken at the same rate as the surrounding terrain, and the edges where the deflected solar wind is focused darken more than average. The result, accumulated over millions of years, is a bright region surrounded by and interlaced with darker material, following the geometry of the magnetic field's deflection pattern. Sinuous, curved, irregular, following the field lines, rather than any topographic feature. A swirl, bright where the magnetic sunscreen blocked the weathering, dark where it focused it. The pattern is a map of a magnetic field that no instrument can directly see, written in differential weathering across the surface, readable as a reflectance pattern from orbit. In November 2024, a paper in Communications Physics presented the most detailed physical simulation of this process, yet achieved a three-dimensional kinetic plasma model that tracked individual ion and electron interactions between the solar wind and the magnetic field geometry at Reiner Gamma. The simulation reproduced the exact shape of the observed swirl pattern from first principles, matching not just the overall bright region, but the specific positions of the darker lanes within it. The curved dark stripes that cut through the bright core of Reiner Gamma and give it its distinctive dot appearance The model confirmed that solar wind deflection is the dominant mechanism, and it answered the long-standing question of why not all magnetic anomalies produce visible swirls, the magnitude, orientation, and spatial configuration of the local electric field all matter, not just the presence of magnetism. In the same year, a separate study used artificial intelligence to analyze the reflectance properties of approximately 130,000 individual boulders in the Rhine Gamma region. Of those, roughly 65,000 showed anomalous properties darker on one side than the other, in a pattern consistent with magnetic sorting of surface dust, accumulating preferentially on certain faces, depending on their orientation relative to the local field. The same physics that creates the large swirl visible from Earth is also operating at the scale of individual boulders a few meters across. Rhine Gamma, seen in full context, is a palimpsest, a surface written over by multiple processes across multiple timescales. The ancient basalt plain beneath it formed 3 to 4 billion years ago. The magnetic anomaly that created the swirl formed during the Moon's dynamo era approximately 4 billion years ago. The differential weathering that made the pattern visible has been accumulating for hundreds of millions to billions of years since the dynamo shut down. And the swirl itself, the bright and dark pattern that Grimaldi saw through his 17th century telescope and couldn't explain, is the accumulated record of all of that history written in the angle at which the surface reflects sunlight. The Moon is in a very precise sense writing its own geological biography on its surface in a language of light and dark, using the physics of magnetism and solar wind as its pen-composing patterns across timescales that dwarf any human framework for duration. But the magnetic story of the Moon is also unexpectedly a story about Earth, because the same tidal interaction that creates moonquakes that drives the Moon's geological activity that slowly transfers energy from Earth's rotation into the Moon's orbit. That same interaction is also responsible for something far more fundamental to the conditions of life on this planet, something so basic that it operates below the threshold of ordinary notice, something that, if it were different by even a moderate degree, would have made the development of complex life on Earth nearly impossible. The Moon doesn't just shape its own geology, it shapes the stability of the planet it orbits. Everything discussed so far has focused on the Moon itself, what's happening inside it, on its surface, across its geological history. But the Moon's most consequential role in the solar system isn't geological. It isn't even about the Moon at all in the most direct sense. It's about what the Moon's gravitational presence does to the planet it orbits, and what the absence of that presence played out over millions of years would mean for the conditions that allowed complex life to emerge on Earth. Earth's axial tilt, the angle between the planet's rotational axis and the plane of its orbit around the Sun, is currently 23.5 degrees. That specific tilt is the reason seasons exist. Because Earth's axis doesn't point straight up relative to its orbit, different hemispheres receive different amounts of direct sunlight at different times of year. In June, the northern hemisphere tilts toward the Sun, more direct sunlight, longer days, summer. In December, it tilts away, less direct sunlight, shorter days, winter. The southern hemisphere experiences the reverse. The entire agricultural calendar of human civilization, the migration patterns of every bird species on Earth, the breeding cycles of marine life tied to seasonal nutrient upwellings, the annual expansion and contraction of polar ice, all of crusted. It runs on the rhythm created by that 23.5 degree tilt. The question that planetary scientists started asking seriously in the 1990s is whether that tilt is stable, not whether it's exactly 23.5 degrees. Everyone knew it varied slightly. That variation is small enough that its effects on climate are gradual and manageable. The deeper question was what keeps it within that narrow range? What prevents it from drifting further? In 1993, the French mathematician Jacques Lascar ran the first detailed computational simulation of Earth's axial behavior over millions of years with and without the Moon's gravitational influence. The method was called frequency map analysis, a technique that identifies the resonance frequencies between a planet's spin precession and its orbital variations. and determines when those resonances are strong enough to drive large changes in axial tilt. Without the Moon, the result was alarming. The gravitational influence of other planets, primarily Venus and Jupiter, both of which exert continuous small perturbations on Earth's orbit, would interact with Earth's spin axis through spin-orbit resonances that the Moon currently prevents. The tilt would not stay near 23.5 degrees. It would begin to drift, slowly at first, then accelerating as it moved through resonance zones. Within a few million years, a geological eye blink, the tilt could reach as high as 85 degrees. At 85 degrees, the planet's axis is nearly horizontal relative to its orbit. The geometry of sunlight reaching the surface changes entirely. The poles receive direct sunlight for half the year, not the oblique, weak sunlight of today's polar summers, but strong, direct, near-perpendicular illumination, the kind that falls on equatorial regions today. Then, for the other half of the year, those same poles are in total darkness, while the equatorial regions cycle between extreme heat and cold. The temperature swings, not gradual seasonal variations, but massive, rapid climate oscillations operating on geological timescales, would cycle through conditions ranging from global glaciation to equatorial scorching. Driven by the wandering axis with no stable equilibrium, Mars provides the closest available observational evidence for what a rocky planet without a large, stabilizing moon looks like over geological time. Mars has two moons, Phobos and Deimos, but they are tiny captured asteroids, negligible in mass relative to Mars itself. Their gravitational influence on Mars's spin axis is essentially zero. Without effective tidal stabilization, Mars's axial tilt has wandered between approximately 10 and 60 degrees over the last few tens of millions of years, with evidence suggesting it has reached as high as 45 degrees or more in the more distant past. The consequences of that wandering are written on Mars's surface. The polar ice caps show layered deposits that record cycles of climate change far more extreme than anything in Earth's quaternary record. The ancient river valleys and lake beds, evidence of a warmer, wetter Mars in the distant past, appear and disappear in the geological record in patterns consistent with repeated radical climate changes driven by obliquity variations. Scientists believe that Mars's inability to maintain stable climate conditions long enough for complex chemistry to develop and persist is one of the primary reasons Mars, despite having had liquid water on its surface, apparently never developed the same trajectory toward biological complexity that Earth followed. The Moon prevents Earth from following Mars's path. The mechanism operates through the same tidal interaction that has appeared throughout this entire story. The Moon's gravity pulls on Earth's equatorial bulge, the slight thickening at the equator, caused by centrifugal force from Earth's rotation in a way that accelerates Earth's axial precession. Earth's axis already precesses it, traces a slow cone in space completing one full precession cycle every 26,000 years, which is why the North Star changes over millennia. The Moon's tidal influence makes that precession slightly faster than it would otherwise be, and that slightly faster precession rate shifts Earth's axial response frequency just enough to avoid the dangerous resonances with Venus and Jupiter's orbital periods that Lascar's calculations identified as the primary codes. Drivers of large obliquity excursions. It's the equivalent of changing the tuning of a guitar string by a small amount to avoid a frequency that would cause it to resonate destructively with a nearby vibration source. The Moon, by its presence and mass at the right orbital distance, keeps Earth's axis tuned to a frequency where it doesn't catastrophically resonate with the rest of the solar system. The result, 23.5 degrees, varying only about 2.5 degrees across hundreds of millions of years, is what made the stable, predictable, seasonally rhythmic climate of Earth possible. And that stability, maintained continuously for hundreds of millions of years, is the backdrop against which complex life evolved. Not just survived, evolved. The development of photosynthesis, the colonization of land, the emergence of forests and their role in oxygenating the atmosphere, the evolution of temperature-sensitive biochemistry that powers all complex metabolism, all of it required climate stability over geological time. Not perfect stability, not no variation, but variation within bounds compatible with continuous biological development. The Moon provided those bounds. It's worth sitting with the architecture of this for a moment. The moon's geological activity, its shrinking, its shaking, its venting, its residual warmth, all of it flows from the tidal interaction with Earth. And that same tidal interaction is also what stabilizes Earth's axial tilt, maintains the seasonal rhythm, and provided the long-term climate consistency that complex life required. These are not two separate stories. They are two expressions of a single gravitational relationship running simultaneously for 4.5 billion years. The moon's geology and Earth's habitability are consequences of the same physics operating in the same system, producing effects that touch everything from the timing of the deep moonquakes 600 kilometers below the lunar surface to the question of why spring arrives at a predictable time every year on Earth. And that relationship is changing. Has been changing since the moment the moon formed. The direction of the change is slow, mathematically precise, and physically irreversible. And what it means played out across geological time leads to the final conclusion that this entire story has been building toward not a discovery, not a mission result, but a number so small it requires laser equipment to measure carrying. Implications that stretch from the deepest past to the far future of the Earth-Moon system. Since 1969, scientists have been measuring the exact distance to the moon with lasers. The setup is elegant in its simplicity. A laser pulse is fired from an observatory on Earth. Several observatories in France, Italy, the United States, and other countries now participate toward a retroreflector left on the lunar surface by Apollo astronauts. A retroreflector is a set of corner cube mirrors engineered to reflect light directly back toward its source, regardless of the angle of incidence, like the reflective beads on road signs that return headlight beams toward the driver, rather than scattering them sideways. The light travels 238,000 miles to the moon, bounces off the mirror, travels 238,000 miles back, and arrives at a detector. The round-trip travel time is measured with atomic precision. The distance is calculated. The measurement is repeated thousands of times across decades of accumulated data. The result has been consistent for over 50 years. The moon is moving away from Earth at a rate of 3.8 centimeters per year. 3.8 centimeters is approximately the rate at which human fingernails grow. In any given year, the moon's distance changes by an amount that would be invisible to any instrument, except the laser setup specifically designed to detect it. 3.8 centimeters against a background distance of 384,000 kilometers is a fractional change so small it has no analog in ordinary human experience of distance. Walking across a room, you would never notice if it had grown by 3.8 centimeters since last year. But the laser measures it faithfully every year, and the number is always approximately the same. The mechanism driving this recession is the same tidal interaction that has appeared at every stage of this story. Earth rotates once every 24 hours. The moon completes one orbit every 27 and a third days. Because Earth spins faster than the moon orbits, the ocean tidal bulges that the moon's gravity raises on Earth's surface are continuously dragged ahead of the moon's position like a tablecloth being pulled across a table, with the heavy centerpiece lagging slightly behind the moving fabric. Those forward displaced water masses exert a gravitational pull on the moon that has a small forward component, a gentle, continuous push in the direction of the moon's orbital motion. That push gradually increases the moon's orbital energy. Higher orbital energy means a larger, slightly higher orbit. The moon moves out. In exchange, the friction between those tidal currents and the ocean floor dissipates energy from Earth's rotation. Earth slows down. The days get longer, not noticeably, not within any human time frame, but measurably relentlessly by approximately 1 to 2 milliseconds per century. The moon gains orbital distance. Earth loses rotational speed. Both effects are imperceptible on human timescales. Both are relentless across geological time. Played backward, the numbers produce a picture of a dramatically different ancient Earth. 70 million years ago, in the late Cretaceous period, a bivalve mollusk called Taurites sanchezi was growing its shell in warm, shallow tropical seas. Like all bivalves, it recorded its growth in daily incremental rings, microscopic layers of calcium carbonate deposited one per day, with slight variations, marking seasonal cycles like tree rings but at daily resolution. A study published in 2020 used laser microscopy to count those rings in fossil specimens and found that during that animal's lifetime, a year contained approximately 372 days, not 365. 372. The year hadn't changed, Earth was still completing the same orbit around the Sun in the same time, but the days were shorter. Earth was spinning faster. The Moon was closer, its tidal braking effect had not yet transferred as much rotational energy away from Earth. 70 million years ago, at the height of the dinosaur era, a day on Earth was approximately 23.5 hours long. Going further back, data from ancient tidal sediment layers in South Africa, rocks from a geological formation called the Moody's Group, deposited 3.2 billion years ago in shallow tidal environments, preserved tidal cycle rhythms in alternating layers of sand and silt. Researchers who analyzed those layers found patterns consistent with a lunar orbit, significantly shorter than today's, implying that 3.2 billion years ago, when life on Earth consisted of nothing more complex than single-celled microorganisms in shallow seas, a day on Earth lasted approximately 17 hours. The Moon was closer. It orbited faster. Its tidal influence was more intense, raising larger tides in the primordial oceans. At the moment of the Moon's formation, 4.5 billion years ago, the Earth-Moon distance was perhaps 1/10 to 1/5 of what it is today, close enough that the tidal bulges the Moon raised on early Earth were enormous by any comparison to modern tides, potentially hundreds of meters high in some ocean geometries, generating tidal currents, violent enough to mix the early ocean's chemistry rapidly and thoroughly. Some researchers have speculated that the powerful tides on early Earth may have played a role in the conditions that allowed the first self-replicating chemical systems, the precursors to life, to develop by concentrating organic molecules in tidal pools that alternately filled and emptied on short cycles. If that speculation is correct, then the Moon's tidal influence didn't just stabilize the conditions for complex life through axial control. It may have helped initiate the conditions for life at the very beginning when the Moon was close and its tidal energy was enormous. Looking forward, the recession continues at 3.8 centimeters per year, and its implications scale proportionally. In approximately 600 million years, a time frame roughly equal to the current age of complex animal life on Earth, the Moon will have receded enough that its apparent diameter in the sky will no longer match the Sun's apparent diameter. The apparent sizes of the Moon and Sun are currently almost precisely equal, a coincidence of orbital distance and relative physical size that is, in geological terms, temporary. Total solar eclipses, where the Moon's disk exactly covers the Sun's disk, revealing the corona and turning day into a brief, eerie darkness, are possible only because of this coincidence. In 600 million years, the Moon will be too small in the sky to fully cover the Sunday. The geometry that makes total solar eclipses possible will end permanently, and every future observer on Earth will see only annular eclipses, a ring of sunlight around a Moon that no longer quite fits across the solar disk. In roughly 1.5 to 2 billion years, the Moon's stabilizing effect on Earth's axial tilt, the mechanism that has maintained the seasonal rhythm throughout the entire history of complex life on Earth, will weaken as the Moon recedes beyond the orbital range where its tidal influence can prevent dangerous obliquity resonances. The same tidal coupling that currently keeps Earth's axis within the narrow range compatible with stable seasons will eventually become too weak to do so. Earth's axis will begin to drift. The seasons will change. The long-term climate stability that complex life has relied upon for hundreds of millions of years will end. That outcome is contingent on the Sun remaining stable, which it won't. The Sun will expand into a red giant in approximately 5 billion years, engulfing the inner solar system long before the Moon's stabilizing effect fully fades. But the sequence of changes driven by lunar recession will begin well before any solar evolution becomes relevant. And understanding that sequence is part of how planetary scientists model the future habitability of Earth and Earth-like planets around other stars. There is a particular quality to this conclusion that only becomes visible when you hold the entire story together at once. The moon is geologically active, shrinking, shaking, venting, gas, retaining heat from a formation event 4.5 billion years ago. It holds water in forms and locations that 40 years of consensus said were impossible. It erupted volcanically within the age of dinosaurs. Its surface records in patterns visible from Earth, on a clear night, the physics of a magnetic field that collapsed billions of years ago. Its gravitational presence has maintained the axial stability that complex life required to develop, and it is leaving 3.8 centimeters per year, measured by laser beams bouncing off mirrors left by astronauts who landed on it over 50 years ago, in missions whose soil samples initially seemed to confirm that nothing was happening there. Every one of those things was simultaneously true in 1969. The moon was shaking under the boots of the astronauts who declared it geologically quiet. It was holding water in its minerals while being described as 100 times drier than the Sahara. It had erupted volcanically in the geological recent past, while being cited as evidence that small rocky worlds go cold and stay cold. And it was drifting away millimeter by annual millimeter, slowly weakening the stabilizing grip that keeps Earth's seasons regular. The moon we understood and the moon that actually exists are not the same object. What the last 15 years of lunar science has demonstrated is not simply that we were wrong about specific facts. It's that the framework we use to interpret those facts, small, rocky world, fast, cooling, simple geological history, one interesting chapter, followed by permanent stasis, was inadequate from the start. The moon's geological activity, its water chemistry, its recent volcanism, its magnetic history, its role in Earth's habitability, its slow recession. None of these fit cleanly into the simple story of a world that burned bright for a dark billion years and then went permanently dark. The moon is still in the middle of its story, not dramatically, not visibly on human timescales, but measurably, in the laser range data, in the seismometer recordings, in the chemical signatures of volcanic glass. Younger than the last dinosaurs in the radon emissions from crater rims that medieval monks watched without knowing what they were, seeing in the bright swirling patterns on ancient lava plains that stumped astronomers for 3.5 centuries. Every time we've pointed a better instrument at the moon, we've found something the previous instruments missed. Every decade of improved observation has added complexity to what had looked from a distance like simplicity. The permanently shadowed craters hold water that has been accumulating since before multicellular life existed on Earth. The sunlit surface holds water that shouldn't be able to survive there. The interior is warm enough to shake, to vent, to possibly still erupt in specific regions. The surface carries the magnetic ghost of a field that collapsed 4 billion years ago, still deflecting the solar wind, still creating bright patterns against the dark plains. A world that stopped doesn't do any of this. The moon was never silent. It was never simple. It was never the dead reference point that 400 years of telescopes looking at a grey disk decided it must be. It was the entire time a world still in motion, moving away from Earth at the speed of a growing fingernail, shaking occasionally in the night, exhaling through its cracks, holding water in the dark and keeping the planet it orbits tilted at, precisely the angle that made it possible for the organisms that eventually evolved on that planet to exist. It's still doing all of this tonight. And in 3.8 centimeters, it will be a little further away.